Okay, let's talk about this idea of address scope. So just like with our IPv4, we have got publicly routable addresses, and then we've got addresses that are designed just to be used within a private network. We have the same setup, the same address allocation for IPv6. So scope can be local or global. So where there is a block of addresses that are designed just to be used within a local routing domain. So in other words, within the company. And there are other addresses which are allocated to be used as globally routed addresses. So if we take a look at, let's just take a look at all the different types of addresses that we use in IPv6. The first is the link local unicast address. So it's a unicast address. Common prefix on all subnets, so it will always start with FE80. They are guaranteed to be unique only on a single link. So in other words, only within a particular subnet are they guaranteed to be unique. And they are generated by the interface itself. So they are automatically assigned. So they are our link local unicast addresses. So I wanted to before we move on to these other ones here, I wanted to just talk a little bit about these link local addresses. Now, the closest thing that we have in IPv4 to this concept is the APIPER address. Okay, so what is an APIPER address in IPv4? Well, that is an address that you see on an interface when you have configured the system to obtain an address from a DHCP server, but for some reason it hasn't been able to obtain an address from a DHCP server. In that case, you'll get an APIPER address, which is an automatically assigned address on the interface. And the purpose of that address is to allow the host that have that address to communicate with each other on the local subnet. Now, the thing with an APIPER address is when you see it, you straight away know that something's gone wrong. For some reason, that particular host can't contact a DHCP server. Okay. Also, when that situation is resolved in that it can contact its DHCP server, that APIPER address is replaced with a DHCP assigned address. So in other words, it gets an address that is part of the IP addressing scheme that you have designed for that organization. Okay, so the APIPER address is gone and the actual DHCP assigned address becomes the address of that interface. So in IPv4, the design of IPv4 is that an address or an interface has one address. It has one IPv4 address. Now, in IPv6, the only similarity to that scenario is the fact that link local addresses are automatically assigned. That's where the similarity ends, okay? Because a link local address does not mean that something has gone wrong. A link local address is an address that an IPv6 interface will normally use, will always use, in fact. A properly functioning IPv6 interface will always have a link local address. And this link local address is a very integral part of the way that IPv6 operates. The protocol itself assigns the address. So it's actually a function within the protocol to automatically assign a link local address on an interface. The link local address then forms a very vital role. It's randomly assigned to begin with. So the 64-bit interface address is a randomly assigned address. The link local address forms a very important function within IPv6 in that it is integral in the protocol that replaces ARP. So remember, what does ARP do? What does ARP do within IPv4? What is the purpose of ARP? What information does an ARP request give us? So why would a host send an ARP request? What information is it seeking? Anyone? ARP request? ARP request means I know the IP address of my destination, but I don't know the MAC address. I don't know the physical address. So an ARP request an ARP request goes out on the network and it says who owns this IP address and what is your MAC address. That's what an ARP request does. And basically, it's a broadcast. The reason it's a broadcast is because the host can't send a frame to the destination host that owns that particular address because it doesn't have the MAC address to put on the frame to send it. So it has to send a broadcast out to the entire network that says who owns this IP address and what's your MAC address, and then the host that actually has that IP address will respond and say, yep, it's me, and here's my MAC address. So that's an ARP request. And if you watch an IPv4 network, you'll see these ARP requests flying around all the time, constantly. So with IPv6, it doesn't send ARP requests, but the link local addresses have a process called neighbor discovery. So they're listening on a multicast. It's a multicast process, and so the link local multi-discovery process will communicate with its neighbors, and it will discover the physical MAC addresses of its neighbors as part of that neighbor discovery process. And part of the process also ensures that the link local address is unique to every machine, every device on the network. So even though they're randomly assigned from a pool, or a 64-bit pool, so there's a lot of numbers in that pool, just in case it happens to randomly assign the same address, even though the odds are, pretty much stacked against that, just in case that happens, there is a mechanism built into this neighbor discovery process to ensure that no other host on the network, no other interface on the network has that same address. So they're generated by the interface, which means that it's actually generated by the protocol. So it's built into IPv6 to generate these link local addresses and assign them onto an interface. So if no other address is ever assigned to an interface, an IPv6 interface will always have a link local address, and it will and communication is enabled on the local subnet by that link local address. The other thing that's different to IPv4 is that a host will always have a link local address, whether or not it has also received another type of address. So we have two other types of addresses that are used. Site local. Site local has actually been renamed. The terminology has been renamed to unique local. But site local is kind of a descriptive name because these types of addresses are really similar in their concept to private addresses in IPv4. So the address is defined by RFC 1918, which is the private address range. So the concept here of these, which are now called unique local addresses, not site locals, so the name has changed. The concept is that you would assign these within a private network in the same way that you would assign a private range of IP4 addresses. So the common prefix is FECO, and with a /48. Why a /48? Well, if you look at the basically the breakdown of it all here, what you generally do is you use the last 16 bits to put a different number on all your different subnets. So the first 48 would generally be the same right across your whole organization, and then you would just have a subnet designator. So you might have subnet 1, subnet 2, subnet 3, whatever, or subnet 10, 20, 30, 40, whatever. So you basically just have a number in there which identifies the particular subnet within your organization. And of course, the interface ID is always 64 bits. So it's kind of like a private address that you would use. Now, of course, when you're thinking about this, well, if I'm using private addresses which cannot be routed on the internet, which they can't, so both link locals and your unique locals are not routable. They cannot be routed on the internet. They're for private use within an organization. So if I'm going to go and assign these, then I am, just by the very nature of it, I am required then to use NATing to go out on the public internet. That's basically, I'm basically committed to it. I'm going to have to implement NATing to go from my private range out onto the public internet. So basically, you will use NATing if that's the way you go. Then we've got our global unicast addresses, which are globally routable on public internet. So they connect to and route through the public internet, similar to IPv4 public addresses. And so we've got the first 48 bits are given to you by either your ISP or a regional registry, where you can just go and apply directly. If you're a large enough organization, you can go and apply directly to the regional registry, get your own block of addresses. Otherwise, you'll just get a block from your ISP. That your ISP will actually give you the first 48 bits. This other 16 bits here is, again, for you to use within your organization. So here's the concept, is that you get a 48-bit block from your ISP. You've now got enough addresses to address each and every host on your entire network, more than enough addresses. And you're going to use this last 16-bit to identify your various subnets within your organization. Okay, so they all have the same 48-bit address, which are all globally routable, but the last 16 bits, you have, okay, subnet 1, subnet 2, subnet 3. So you'll just basically use that there. So you might just have the first 48 bits, whatever you've given, followed by ::1, and then you'll have another next network, ::2, ::3, ::4, and you'll just basically identify all your subnets in that way. So when you think about it, it's not that hard. Like, even though we've got this massive 128-bit address, okay, you could say quite simply, well, I've got subnet 1, subnet 2, subnet 3, subnet 4, and the first 48 bits of all those subnets are going to be the same. The only thing that's different is the last 16, and quite frankly, you could do that with a : :1, : :2, : :3, to very easily sort of map out an addressing scheme. So when you think about it, it's not really all that complicated. So what about the interface ID? We'll get to that, okay, as to how we come up with that. So there's our 3 blocks. Now, when you go and apply a global unicast address, or even the unique local address, you will still have a link local. So in other words, you're going to have 2 addresses on an interface. 2 addresses. You'll have a link local and potentially a global unicast address on the interface. The link local is needed. So link local is part of this neighbor discovery process. That's an integral part of how IPv6 is working. Okay, so its internal workings of IPv6 require the link local address. So you will have, if you go and assign your global unicast, you will have a link local address on the interface as well. So that's different. That's quite different to IPv4. Okay, let's take a look at the interface ID itself, which of course identifies the host on the subnet, which of course must be unique on every host on the subnet, is 64 bits long. So how do we get this assigned then without using a DHCP server? We're not going to use a DHCP server on our network. We don't really need one with IPv6. Fortunately, we have this addressing scheme called IEEE EUI64. And what that essentially does is it takes a look at the host that requires an address. It says, well, you've already got a MAC address. That's already a hexadecimal number, and it's already unique to every single host on the network. So in effect, there is a unique element, there is a unique hexadecimal number already assigned to every host on the network. Can we use that to give us a unique IPv6 address for every host on the network? Yes, we can. All we need is another 16 bits, and we're there. Okay, so basically, what we do is we take the MAC address, which is the interface identifier, put another 16 bits right in the middle of it, and there's our unique IPv6 64-bit address done. Okay, that process is known as EUI64, address allocation. So what about the first 64 bits? Where's that come from? Well, glad you asked. Let's have a look at the process whereby this happens. So we're talking about stateless auto configuration. So it allows hosts to auto configure IPv6 addresses, eliminates the need for stateful configuration elements such as DHCP. We don't need a DHCP server at all. So what is the process? How does this happen? Well, we have this process where we go through, we have a extended unique identifier. So that, in other words, we take the MAC address, which is our unique identifier, we add an extra 16 bits to it. That extends it out to 64 bits. That becomes the interface IP address, or the host part of the IP address. We use these things called router advertisements and router solicitations to communicate and to assign both the prefix, which is the network number, and to instruct the host to create this unique identifier, this extended unique identifier. And of course, we have a prefix list, which is our network number. We also have this neighbor discovery process, which I mentioned earlier, process of tracking reachability status in neighbors in a local link. This process uses the link local address. So it is really the link local address that's integral to the neighbor discovery process. Okay, so let's take a look again at this stateless auto configuration. So here we have our router. In this case, this router also looks like it's a gateway as well. So here's our router. We've got host A has got a MAC address of 1234 ABCD 5678. Host B has got a MAC address of 9876 DCBA 5432. Okay, so here we have two hosts, obviously different MAC addresses. So what we're going to do, first thing that happens is IPv6 comes up and it will automatically assign a link local address to each of those hosts. So that's something the hosts are going to have that no matter what. Even if they have no other address, they're going to have that. That's just an address which is assigned onto the host. By the way, the link local address doesn't have to be tied into the MAC address. It can just be a randomly assigned address as well. Then we have a router solicitation. So the host comes up and it says, okay, I'm looking for a router, and that's a multicast transmission that goes out. So what you've got is IPv6 routers are listening on that multicast address for these router solicitations. So what's happening is the host is looking for its gateways. It basically has to find out where's my default gateway on this network. So it sends out this router solicitation saying, hey, any routers out there that are going to be my default gateway. And the router will receive that, and it will respond. Here it comes out, step 3. It's going to respond with this router advertisement. Okay, now think about router advertisements. Routers send these out periodically, whether or not they ever received a router solicitation. So they do send these advertisements out anyway. So the advertisement has some information in it. What it has is, first of all, it has the prefix, the network prefix. So the router will distribute, obviously the interface on the router is configured with a 64-bit network number, okay, which includes the 48 bits that you may have got from your ISP, plus your 16 bits, which identifies your particular subnet. So it'll send that out, but then it will also send out this EUI64 configuration, where it will say, okay, I'm going to use your MAC address, and I'm going to then include an extra 16 bits into that address to give you a unique IP address for your interface. Okay, so here we have, without the need for DHCP, the ability to assign a unique IP address, IPv6 address, to each and every interface on every device. So we've got the first 64 bits from the router interface itself, and the last 64 bits, we've got that from the MAC address of the device, plus we've added an extra 16 bits in just to pad that out to 64. Okay, there is the ability, if you really want to have DHCP, okay, even though it's absolutely not needed. One of the early concepts around this, and this has kind of been superseded in some way, one of the early concepts was, oh, well, you need DHCP because you need to assign, you need to inform the client as to where their DHCP server is. Okay, so far, if we go back to the previous slide here, we say that what we've done is we've been able to inform the host as to what the address of their router is. So part of this RA that comes back is, hey, I'm your default gateway. This is my address, so we can configure a default gateway. And here's your network number, and here is your host portion of your IP address, IPv6 address, based on your MAC address. So we can inform the host of its default gateway and assign a unique IPv6 address onto the host. But hey, where's the DNS server? A host is going to need that information, isn't it? It's going to need to know, where's my DNS server? The original thought was, well, we might have to have a DHCP server to actually do that. But in actual fact, we have got an ability to go ahead and do that without a DHCP server. I just want to show you some information. It's going to pop up on screen. First of all, I'm going to pop up this this RFC here, it was a draft, but basically it goes through the process of how you can assign, using this neighbor discovery, using this router solicitation process, part of this process, of how do we assign DHCP information to a host. And it goes through and describes in quite a bit of detail this process of RDNS, which is basically stands for Recursive DNS Server. And how is this information provided? It's provided through these router advertisements and solicitations. So that is the process by which it is, in fact, provided. This obviously goes through in a fair bit of detail, goes and explains how that works. Now, from a point of view of how do I actually configure that, we've got information right here as to how to go ahead and configure a recursive DNS server address for IPv6 hosts onto your router. This is a Juniper router, and the process there of how do you go ahead and put that information onto your router advertisement. So here it is, edit protocols, router advertisement, and set interface name, DNS server address. So you put 3 DNS server addresses. So what you're effectively doing is you're including in your router advertisement 3 DNS servers, which are then advertised out to the hosts. So what we're doing is we're absolutely doing away with the need for a DHCP server altogether. Okay, so all of that functionality is handled by the router itself. So the router itself now is going to come up and say, okay, I'm your default gateway, here's my address, this is your network portion of your IP address, and here is your host portion based on your MAC address plus an extra 16 bits, and here is your DNS server address. So all that is contained now within this RA, this router advertisement. Okay, so initially it was thought, oh well, we need a DHCP server, but fortunately this router advertisement has been expanded to incorporate that information as well. So really you don't need a DHCP server at all in IPv6. Okay, so we've had a look at some of the concepts here. So what have we discovered? We've discovered that we're always going to have a linked local address, even though we may have a unique local and a global address on there, a unique global address. We're always going to have a linked local. So quite commonly, we'll have 2 addresses on an interface. That goes for a router interface as well as a host interface. We've discovered that the addresses can be assigned by the router using EUI64. We've discovered that we're going to have the first 48 bits are going to be the same probably for our entire network, and we're going to use the next 16 bits of the network number to identify our subnets. So basically that takes care of our addressing scheme. So it's not that complicated. It's quite easy just to say subnet 1, subnet 2, subnet 3, etc. And we can quite easily, as I said, have our host address assigned using EUI64. So let's have a look at the config here. So here we are looking at our interface config. Notice that the family INET 6 rather than INET, which should be IPv4, and the address is a hexadecimal number. You know, so we just got ::1 to identify the last 64 bits in actual fact of our address. So we've got the first 64 bits. This is actually a unique local address there, and then we've got /64 on that. So it's always /64. Okay, it's never anything else. And then we've got another interface there with its interface 2. So interface 1, interface address 2, and that's a unique local address. Okay, we do a show interface terse. It's the same command. Like if we were doing this on a Cisco router, you'd have to type in show IPv6 interface brief. But on a Juniper, it's just show interface. You don't have to specify the protocol, and it'll just show you all the addresses. So if we've got IPv4 there, they'll come up, and so will IPv6. It'll just show you all of those addresses. So you will notice that every address is going to have its own link local address. Well, it'll actually have a link local as well as a unique local. So that will actually come up as well. So there's our link locals. And if we're assigning a unique local, and then that will come up, or if we're assigning a global address, that will come up as well. So you'll commonly see multiple addresses on an IPv6 interface. That would be normal. So this is routing information. Show is our show route table INET6, and we can go ahead and see our routing information in there. Want to use the ping command. We can do a show IPv6 neighbors command, and we can also do a ping command there. Okay, IPv6 multicast addresses, same as IPv4, they identify a group of nodes. Members of a multicast group process incoming packets. It's more efficient than broadcast. 3 types of multicast addresses. There are these listed as node multicast address for neighbor discovery, all nodes multicast address for router advertisement, and all routers multicast address for router solicitation. So routers and hosts are listening on these addresses all the time as part of the IPv6 process. We also have this anycast address, which is identifier for a set of addresses typically belong to separate nodes. RFC 2526 describes that. The packet travels to just one of the interfaces identified in the group. It's actually the closest one. So it's the one that receives the traffic first. So that's our anycast. Let's take a bit of a look at configuration of IPv6. Want to configure a static route. Here is a static route here. You notice that we've just got route 0::0, and we've got the next hop there. You can set a preference. The usual preference on a static route, the default preference on a static route would be 5. You just set it to a higher preference here, as you can do. You don't have to change the preference. It'll work perfectly well without changing the preference, but you can change it if you want to, if you need to. Show route table INET6 will show us the contents of our routing table. This is we can also specify a protocol as our static routes here. So there's our default static route, IPv6 default static route that we've set up there. OSPF. It's OSPF version 3 that is the version that is compatible with IPv6. So if we're going to look at our configuration here for IPv6, one thing to note straight up is that our router ID is manually configured. Okay, and it is a dotted decimal notation. So your router ID, you have to manually configure it, as I mentioned earlier, in IPv6, because we cannot use a hexadecimal number as a router ID. So we can't go ahead and set our loopback address with a IPv6 address and have that become the router ID. We just can't do it. So if you're using IPv6 right through, you've got to manually set your router ID. with setting up our protocol here. We've got show protocols OSPF 3. So we've included our interfaces under the OSPF 3 protocol. And when we're taking a look at protocols, we'll go show protocols OSPF 3. So instead of OSPF, it's OSPF 3. Same goes for neighbors and the other commands that we kind of use with OSPF version 3. You do put the 3 after the OSPF. Look at your neighbors, interfaces, database, and routes. Different protocols for using ISIS, pretty much the same for IPv4 and IPv6. Haven't really got into ISPF. The family ISO is what identifies the ISIS protocol, and then we're simply putting those IPv6 addresses on the interfaces as usual. Same operational commands for ISIS. So regardless of whether we're using IPv4 or IPv6, the same command. So you don't have to go ISIS 6 like you did with OSPF. BGP configuration, almost identical for IPv6 as it is for IPv4. Major differences you specify an IPv6 address for the local and peer addresses. So it's the only difference. So there's our local address, our neighbor address, which is our peer address for our internal group. So that's the only difference, of course, is the fact that we're using IPv6 addresses. Otherwise, it's the same. Router ID, you'll notice, has got a dotted decimal address. Same for operational commands, exactly the same. Show BGP summary, and we'll see the addresses there. Okay, so I don't want to get into tunneling, mainly because it's sort of a kind of a band-aid sort of a thing as to, you know, okay, how do we get? The idea is we've got a native IPv4 network, but we want to connect two IPv6 networks together through this native IPv4 network. How do we do it? There are kind of other ways of doing it other than tunneling, using dual stack networks that support both 6 and 4 and can quite easily accommodate both of those protocols. It's a much better way than actually doing tunneling. So what we'll do is we're going to have a break there, and when we come back, we want to take a look at class of service.